Hi, welcome to AlgoMithr, your friendly guide to sizing up tricky algorithms. Our goal today is to try and understand the KMP algorithm. Uh, KMP algorithm is one way to implement a string finding function, that is a function that takes in two arguments and two strings basically, and returns the location of the first string if it is present in the second string. So here we are calling those strings as part and text. So the part is presumably the smallest string, which we are trying to see if it's present in this presumably larger string text. And if that is so, we return the first location of part in text, or we return -1. Who is this video meant for? This is meant for those who are good in coding but probably are a bit rusty with their recursive thinking and also algorithms. So, and also for those who have trouble understanding this particular algorithm just because of the kind of example test data that is used. So usually when the KMP algorithm is provides efficiency for situations where there is a lot of repeating patterns in the input strings. So the examples usually are like follow the suit, and hence they are usually a string of repeating characters. So that can get confusing for some. So for those, the watching this video could be advantageous because we just use very simple, intuitive words like we start with example. That's one string in our test data. Then we use other strings like Coco, COCOA. We use strings like baby and mama, and that's it. So that's one thing that I guess would help some of you. So let's get our first version done right away. It's a simple problem, right? After all, we just have to see if the first string is part of another string or not. So before we do that, before we do our first version, the first implementation of find it function, I'm just showing you here the standard KMP algorithm published by the geniuses in way back in 1977, and this is all of the algorithm, just this. So you can just pause the video, take a good look at it, and maybe you're just done then. So if you get it, then that's it. Good for you. But for others, after giving this good thought, and if you read a little bit more intuitive development, uh, or a path which gradually leads you to here, then maybe you can just stay tuned. So let's get our first version done right away. And what were we doing? What were we supposed to do? We were supposed to implement this function. Find it takes in two arguments, part and text, and returns the position, the first occurrence of part in text. But for now, we just return -1. And we also need a way to test our function. So we'll keep it simple here. What we'll do is we will just output the result of the function. So we invoke this function, find it. You can do it in several ways. Here I'm just choosing to define two strings, part and text, in the main, and read them of the standard input. So there we get the part, and then there we get the text. And how about some test data for us to test our program? We start here with a simple word example, and we try to check if the word ample is present in this other word example or not. So here we read part, ample into part, and here we read example into text, and then we invoke our function, and we would expect it to be 0, 1 and 2 to be the value. Let's just test it without implementing. We should get -1. So here we have -1. Now I would encourage you to get your pencil and paper or slate and chalk or whatever, and also pull up your programming environment and do this in tandem. So I guess that's the only way to actually learn, right? So if you're just watching the video and not coding, I think it's in my humble opinion, I think it's a waste of your time. So please try to implement this function on your own. You can pause the video now, and then once you're done, we'll just go along from there. So I hope you're done with your implementation. I'll begin mine here now. So before I do anything, I get the lengths of part and text into two variables, m and n. This would help us assess the complexity of the function later, and also probably keep our function a little bit more neater instead of using this text.length in the body of the function. What's the strategy? How are we going to do this? How are we going to check if part is in text or not? So one foolproof way is to check is to see that if part is present in text, right? If part is present in text, it has got to start somewhere within text, right? So it could start at the very beginning of text, or it could start at the very end, the last character of text. But this seems to be a proper bound, correct condition. But would this be the case? This could be the case only when part is just one character, right? So if part has to begin, if we are looking at this particular variable I, as we are scanning through the text, if I has to be the beginning of part, then it's probably m-1 character still has to go after it, right? So otherwise you can't have m characters beginning at position I. So that's the logic of fixing this bound here, right? So our main logic or argument towards the correctness of our first implementation is that if we have to find part in text, it has got to start somewhere, right? So if we find that somewhere starting in text, and then try to also match the subsequent characters from there, and if we have a match, then that is going to be the location of part in text, and it cannot possibly go wrong, right? So what we do then, we try to see if part begins at that particular location that we are at currently in text. So we see a beginning, for example, if we are in this if block, then we see a beginning. Then what do? We go ahead and check. Here I'm building, or I'm creating one more index into text, starting at the very subsequent character after where we have found part, and another index into part starting at its second position. I mean, index wise it's 1, but the second character. So, and we try to match all the subsequent characters. So here our bound is we obviously should not run over the part, the length of part. And then we do this as long as we have characters in part matching the subsequent characters in text. If this is happening, we are really happy. So we just keep going on and on till we run out of all the characters in part. Now if that's the case, then k would have gone all the way up till m. So here we have a match, right? So we matched all the subsequent characters in part with all the subsequent characters in text. And if we hit this, which means the position I is the position where we have part started, and that's emphasized by basically this entry point into this block itself. So as we have programmed, we have also argued about its correctness. So we return I here, and if not, then we don't have any match, so we return -1. Now let's review our input to see if it has stayed the same. We are trying to find the word ample in the text example, and earlier we had an incorrect result because we pretty much had an empty function. Now let's run this, and here, as we expect, we have a result. It says ample is found at location 2, and that is a correct answer, right? So just to test out, I mean, theoretically we have argued the correctness of this program, but just to test out, we can insert some partial matches into our text data. Like here I'm inserting AM, AMP, AMP, L, and then finally we have this ample here at the very end, right? So just to see that our function doesn't goof up. As expected, it seems to work correctly. So this seems to work pretty fine, but when it comes to the complexity, you can see that it has a quadratic complexity. The number of times the outer loop runs is close to n, and the number of times the inner loop runs is close to m. So overall, we have a complexity of nm. This is the worst case complexity. It depends on the test. It depends on the test data, though, right? So when will we really hit nm? We'll do that when the text is just repetitions of part, right? So we have, for example, we have this. For example, if we have something like, I guess, just look at the bottom of your screen where I'm changing the input, right? So if you have something like ample, 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 I don't know, goes forever, and then finally you have the full match. That's when you're going through, this k less than m times. Right? That's when you're really, burning all your oil here all the time. So this may be usual or unusual input. We cannot really judge that. It depends on the application, right? So if your application in the foreseeable future does not have this kind of, does not have to consistently deal with this type of data here, right, then probably the function that we have implemented here is good enough, right? Maximum, let's say, if we assume that only the first two characters match, or maximum you will have a repetitions of sizable substrings like 3 or 4 times, then it's okay to pay the little price. But if it's consistently be going to this type of input, then of course we have to optimize. We have to think of ways to optimize our implementation. But before we do that, maybe we'll just go to the whiteboard and look at how we can, where the inefficiency is coming from. Of course, we can see it here, the double loop, but try to see if we can somehow improve it.